Hello everyone, my
Yes.
name is Harikesh Patel and today we are talking about design and implementation of finite state machines in digital system. The first question is what is FSM? FSM stands for a finite state machine which is a computational models used in computer science engineering and various other fields to represent a system with a finite number of states. Second, more important question is why use FSM in digital system? Finite state machines are fundamental concept in the design of digital system, providing a powerful abstraction for modeling sequential logic and current control flow. They are widely employed in digital logic circuit, embedded system, and computer programs to manage complex behavior and decision-making process. An FSM consists of key components such as a finite set of states, input signals, output signals, and transitions that dictate the movement between state based on or input condition. Types of FSMs. There are two types of FSM. First is mode FSM. What is mode FSM? Mode FSM is a type of finite state machines where the output depends only on the current state, not on the input directly. Mode FSMs more stable because output change only on state transition. Example of the mode FSM is a sequence detector where output is activated when a pattern is matched. In a sequence detector is a finite state machine that recognizes a specific sequence of bits in a stream of input data. When the FSM detects the target sequence, it activates an output signal. Second type of FSM is a milli FSM. A milli FSM is a type of finite state machine where the output depends on both the current state and the input. This allows the machine to respond faster since output can change immediately based on input. M- Milli FSM is a more responsive as outputs change instantly with inputs. An example of milli FSM is a vending machine. A vending machine can be modeled as a finite state machine where the output means dispensing an item depends on both the inserted coin and the current state. FSM fundamentals. There are two types of FSM fundamentals. First one is states and second is transitions. What is state definition? A distinct condition or mode within FSM. Each state detects how the system responds to inputs. It means a state in a finite state machine represent a condition of the system at a specific moment. In a milli FSM, the output depends on both the state and the input. And second is a transition definition. The movement from one state to another. Transitions are triggered by specific input conditions or event. It means a state transition defines how to FSM moves from one state to another based on inputs in a milli FSM. The transition also determines the output as it depends on both the current state and input. FSM design methodologies. First is requirements analysis. Thoroughly analysis and define system requirements and behavioral specification. Second is state diagram creation. Into a clear and concise visual state diagram. Third is state minimization. Optimize the FSM by reducing the number of states while preserving core functionality. One more topic, hardware implementation of FSMs. First is combinational logic. Implement transition logic using AND or NOT gates. In combinational logic is used for two main purposes. First is next state logic. Determines the next state based on the current state and input. And second is output logic. Output logic generates the output based on the mode FSMs or milli FSMs. Second type of implementation of FSMs is sequential logic. Use flip-flops to store the current state. Sequential logic in a finite state machine is responsible for storing and updating the state logic state of the system, unlike combinational logic, which depends only on current input. Sequential logic relies on memory and a clock signal to track past states and determine the next state. Third type of implementation of FSMs is FMS architecture. Connect logic and flip-flops for state transition. A finite state machine architecture consists of three main components. First is state register, means sequential logic stores the current state. Second is next state. Logic means combinational logic determines the next state based on inputs. Third one is output logic. Uh, uh, Output logic generates output based on states and inputs. Uh, uh, Topic is software implementation of FSMs. First is FSM representation. FSM can be represented in different ways depending on the context and design needs. The most common representation include: first is state diagram, second is state transition table, third one is state encoding, means binary representation, and fourth is FSM description in hardware description language. Second type of implementation of FSMs in software: conditional statement. Conditional statements in an FSM determine: first is a state transitions, moving from one state to another based on input condition, or output, generating output based on more FSM or milli FSM. Conditional statements are typically implemented using if-else statements or case statements. Third is interrupt-driven FSMs. Uh, Interrupt-driven FSMs and a driven FMS is a finite state machine that responds to external interrupts rather than continuously checking for inputs. This is useful in event-driven system where the FSM transitions occur only when an interrupt occurs, improving efficiency and reducing power consumption. State, the topic about state encoding techniques. There are three types of state encoding techniques. First is binary encoding, minimizes flip-flops and complex logic. Second is gray code encoding, reducing switching activities and glitches. And third one is one-hot encoding, simplifies logic, requires more flip-flops. FSM optimized techniques. First is state minimization. State minimization reduces the number of states to simplify the FSM while preserving its functionality, leading to reduced and hardware requirements. Second is logic optimization. Logic optimization minimizes the complexity of combinational logic used for state transitions, reducing gate count and propagation delay. Third is clock gating. Reduce power consumption by disabling the clock gating parts of FSMs, improving energy efficiency. There are applications of FSMs in digital systems. First is control system. In elevators, washing machines, and traffic light controllers, we use FSMs. Second is communication protocols. UART, I2C, and SPI, TCP or IP for data transmission. We use FMS in digital system. Third one is microprocessor and embedded systems. In microprocessor and embedded system, instruction decoding or power management. And fourth is industrial automation, conveyor belts, robotic arms, security system. We use FSMs in these types of applications. FSM design challenges and solution. First one is state explosion problem. Large FSMs require many states, and its solution use hierarchical FSMs or microprogramming. Second is glitches in output. Asynchronous transitions cause glitches, and its solution is use proper clock synchronization. Third one is implementation complexity. Large FSMs require more flip-flops and logic gates, and its solution optimized using state minimization technology. Advantages of FSMs. First is predictable and well-defined behavior. FSMs follow a predefined sequence of states, ensuring that system behavior is always predictable and easy to understand. Second is simplifies complex system design. FSMs break down the problem into states and transitions, making complex logic easier to manage and design. Third one is efficient use of hardware resource. FSMs optimize flip-flop and logic gate uses, reducing the need for excessive hardware components. Fourth is easy debugging and testing since FSM operate in well-defined state. Debugging and fault detection become straightforward compared to unstructured sequential circuit. Uh, Scalability and reusability. FSM can be expanded to handle more states and functionalities. The same FSM models can also be reused in different applications. FSM components. First is states. State represent different operating modes. Second is input. Input external signals affecting state transition. Third one is output. System behavior based on the state or input. Fourth is state transition logic. State transition logic defines state to state movement. And fifth is clock signal. Clock signals synchronizes transitions. Limitations of FSMs. First is a state explosion problem issue. As system complexity increases, the number of state grows exponentially, making the FSM difficult to manage. And its solution is use hierarchical FSMs or state minimization techniques to reduce complexity. Second is memory consumption issue. Large FSMs require more flip-flop and memory to store state information. And its solution is use optimized state encoding techniques like one-hot encoding or gray code encoding to reduce memory usage. Third is difficult to modify and expand issue. Adding new feature to an existing FSM can be complex as it may require modifying multiple can states and transition. And its solution is designed FSM in a modular way to allow easier modification. Uh, Fourth is asynchronous transition issue. In Melee FSM, output depends on inputs, which can cause glitches if inputs change unexpectedly. And its solution is use proper clock synchronization and debouncing techniques for stable transitions. Fifth one is implementation complexity for large system issue. When designing highly complex system, FSM may require a large number of gates, making implementation difficult. And its solution is use alternative approaches like microcontrollers, microprocessors, or software-based state machines for complex applications. A case study 1. Traffic light controller and requirements. Manage traffic flow using timed transitions based on safety protocols and real-time traffic density. Optimize traffic flow at intersections by dynamically adjusting light timings to minimize congestions and ensure safety. Second is FSM design in traffic light controller. Establish states and transitions triggered by timers and input from traffic sensors. Create a detailed state diagram accurately representing the traffic lights operations behave under diverse traffic scenarios. Implementation of traffic light controller. Deploy the controller using a microcontroller of FPGA, ensuring a precise timing controller. Develop firmware to oversee state transitions and process sensor data for adaptive traffic management. Traffic light FMS, FSM cycle through red to green, green to yellow, and yellow to red state. Uh, there are a table of traffic light FMS cycle, current state, input, next state, or output. In a current state, first one is red, and its input is 1. Then, then next state is green, or output of the first state is a red. Second current state is a green, and their output is a 1. Or uh, green next state is yellow, or for second state's output is green. Third one is yellow, and its output is 1. Or its next state is red, or output is third state is yellow. This is the cycle of the red to green, green to yellow, or yellow to red. Second case study is a vending machine controller. Its requirements is requirements. The vending machine must accurately accept the validated coins, ensuring sufficient funds for the selected product. It needs to dispense the product and provide correct change, managing transactions efficiently from start to finish. FSM design. Design state to manage the vending machine's operations, including idle, coin insertion, product selection, dispensing, change dispensing, and error handling. The design should handle various inputs such as coin values, product choice, and error conditions like insufficient funds or unavailable items. Fourth one is implementation. Implement the controller using a microcontroller or programmable logic device. Integrate sensors for accurate coin and product detection, and use actuators for dispensing items and change reliable. Ensure robust performance and error and handling through careful programming and hardware integration. Case study 3 is FMS FSM based the digital door lock system. Background is a digital door lock system requires a 4-digit passcode. The system must first one is accept the user input, second one is verify the enter passcode, third one is unlock the door if the passcode is correct, and fourth one is lock the system if the wrong passcode is entered 3 times. FSM design steps in a door lock system. Step 1 is identify states. First one is idle state. Idle state is a waiting for user input. Second state is a input state. Input state accepting passcode digits. Third state is verification state. Verification states including checking passcode validity. Fourth state is access granted. Access granted is unlocking the door. State 5 is access denied. Access denied locking the system after 3 failed attempts. Step 2 is state transition diagram. State 0 to state 1, state 1 to state 2, state 2 to state 3, and if state 3 is passed, unlock the door. Otherwise, state 4 is fail after 3 attempts. Locked. There are diagram of the state transition. Lock the initial state. Correct a passcode. If the correct passcode, unlock the door. Otherwise, lock the door. And after the fail after 3 attempts, lock the door. Step 3 is state transition table. Current state is state 0. It's an idle state. And there user starts input. If the input and output is waiting for the input. State 1 is input. State 1 is input, and uh, there user entered the 4-digit code, and the next state is verifying the code. State 2 is verifying the code, and if the code matches, state 3 is unlock the door. If the unlock the door, state 2 verify code incorrect 3 tries, state 4 is system locked. state 4 locked, reset pressed, and system state 0 reset to idle. Implementation consideration: use flip-flops for state storage, uses combinational logic for transitions, clock signals synchronizes state changes, and its outcomes is the FSM successfully implements a secure automated door lock system. And second is ensure controlled access and prevents the unauthorized entry. And the conclusion of advantage and applications. First is simplicity. FSMs offer a clear and intuitive framework for designing digital systems, making them easier to understand and maintain over time. Second is modularity. Modularity: by promoting a modular design approach, FSMs enable to division of complex system into distinct manageable states, enhancing reusability and scalability. And third is easy of implementation. FSM can be implemented in both hardware and software designers with flexibility in choosing the optimal optimal implementation architecture and deployment strategies.